Observing what's happening, as we did in the last section, gives us a way to predict performance, but it really doesn't help us understand what the algorithm's doing. So next we're going to look at mathematical model, a way to get a better concept of what's really happening. Again, this concept was really developed and popularized by Donald Knuth starting in the late 60s. At that time, computer systems were really becoming complicated for the first time, and computer scientists were concerned about whether we really were going to be able to understand what's going on. And Knuth was very direct in saying that this is something that we certainly can do. We can calculate the total running time of a program by identifying all the basic operations, figuring out the cost, figuring out the frequency of execution, and summing up the cost times frequency for all the operations. You have to analyze the program to determine what set of operations, and the cost depends on the machine and the computer in the system, is what we talked about before. The frequency leads us to mathematics because it depends on the algorithm and the input data. Knuth has written a series of books that give very detailed and exact analyses within a particular computer model for a wide range of algorithms. So from Knuth, we know that in principle we can get accurate mathematical models for the performance of algorithms or programs in operation. All right, so what does this process look like? You can, if you want, run experiments. In ancient times, we would actually look at the computer manual, and every computer came with a manual that said precisely how long each instruction would take. Nowadays, it's a little more complicated, so we run experiments. And you can go ahead and do 1 billion ads and figure out that maybe on your computer an ad takes 2.1 nanoseconds. Or you can do more complicated functions like compute a sine or an arctangent, although that's already getting close to the analysis of algorithms. So there's some way to determine the cost of the basic operations. So we'll just, in most of the cases, we'll just postulate that it's some constant, and you can figure out what the constant is. Although when we're working with a collection of objects, of n objects, there's some things that take time proportional to n. Like if you're going to allocate an array of size n, it takes time proportional to n because in Java the default is that all the elements in the array are initialized to 0. In other operations, it depends on the system implementation. And an important one is string concatenation. If you concatenate 2 strings, the running time is proportional to the length of the string. And many novices programming in Java make the mistake of assuming that that's a constant time operation when it's not. All right, so that's the cost of each operation. More interesting is the frequency of operation, of execution of the operations. So this is a very simple variant of the 3-sum problem. That's the 1-sum problem. That's how many numbers are actually equal to 0, how many single numbers add up to 0. So that one is just one for loop, and we go through and we test if the number is 0 and increment our count. And by analyzing that code, you can see that I and count have to be declared, and they have to be assigned to 0. There's compares of I against n, and there's n plus 1 of them. There's compares of a of I against 0. There's n of those, n array accesses. And the number incremented is, number of times as an increment is variable. I is incremented n times, but count could be incremented any number from 0 to n times. And so that frequency is dependent on the input data. We might need a model for describing that, or maybe there's other operations that are more expensive and we won't need to worry about that. So let's look at next more complicated problem is what about the frequency of execution of instructions in this program, which is the 2-sum problem. How many pairs of integers sum to 0? Well, in this case, you have to do a little bit of math to see that when I goes from 0 to n and j goes from I plus 1 to n, the number of compares that we do, or let's say array accesses that we do, is 2 for each time the if statement is executed for ai and aj, and that time thing is executed n minus 1 times the first time through the loop, and n minus 2 the second, and so forth. It's the sum of the integers from 0 up to n minus 1, which is a simple discrete sum, 1/2 n times n minus 1, and since we're doing it twice, the number of array accesses is n minus 1. So we can go ahead and get these actual exact counts, but already it's getting a little bit tedious to do that. As far back as Turing, who also knew that, as well as Babbage did, that we want to have a measure of the amount of work involved in the process, he recognized that you didn't want to necessarily go through and do it in full detail. It's still helpful to have a crude estimate. So you could count up the number of times that every operation is applied, give it weights, and count the subtract and so forth. But maybe we should just count the ones that are most expensive. That's what Turing said in 1947. And realistically, that's what we do nowadays. So rather than going in and counting every little detail, we take some basic operation that's maybe the most expensive and or the one that's executed the most often, the one that cost times frequency is the highest, and use that as a proxy for the running time. Essentially making the hypothesis that the running time is going to grow like a constant times that. So in this case, we're going to pick array accesses. So that's the first simplification. And the second simplification is that we're going to ignore low-order terms in the formulas that we derive. And there's an easy way to do that. It's called the tilde notation. And the idea is when n is large in a formula like this, the n cubed term is much, much higher than the n term, or 16. In fact, so much so that we wouldn't even would hardly notice these low order terms. So all of these formulas are tilde 1/6 n cubed. And that's a fine representative or approximation to these quantities. And it greatly simplifies the calculations to throw away the low order terms like this. So by focusing on one operation and throwing away the tildes, the low order terms, and this is the technical definition of tilde, it just, f of n tilde g of n means the limit as fn or gn equals 1, and you can check that that's going to hold in these kinds of situations. So that greatly simplifies the frequency counts, and if we're only picking one thing, we're just talking about tilde n squared and maybe another tilde n squared for the increment for the two-sum problem, say. So again, when n is large, the terms are negligible. When n is really small, they're not negligible, but we don't really care because we're trying to estimate running times for large n, and running times for small n are going to be small no matter what. All right, so now we're using both the cost model and the tilde notation, and then we can simply say that this program uses tilde n squared array accesses and have implicit the hypothesis that we think the running time is going to be tilde a constant times n squared. Okay, well now what about three-sum? Let's do our real problem. So now we have the triple loop. And then we have to do a more complicated combinatorial problem. And it's not that big a deal, really. We're looking at the distinct number of ways you can choose three things out of n, and that's the binomial coefficient. And again, doing the math and using the tilde, it's just tilde 1/6 n cubed. 3 array accesses for each triple, so we can say half n cubed. We're not computing and summing the costs of all operations. That's too much work. We're picking the most expensive in terms of cost times frequency and approximating that and trying to get a good model for the running time. Now, we're not going to do a full discrete mathematics in this course, but there's some basic things that we'll want to use and are not that difficult to understand. So a lot of times we find out that we need to come up with an estimate of a discrete sum, like we did for 1 plus 2 up to n, or some of the squares, or other things like the three-sum triple loop. And so actually, if you've had basic calculus, one way to think of it is to just replace the sum with an integral. That usually works, or we can do the math and use the so-called Euler-Maclaurin summation formula to get a true approximation. But if you think of it this way, you'll believe us when we say that that thing is tilde half n squared, or sum of 1 plus 1/2 plus 1/3 up to 1 over n. That's like integral from x equals 1 to n 1 over x, and that's natural log of n. Even the three-sum triple loop, if you're used to multiple integrals, will quickly give you the 1/6 n cubed. There's many more and other techniques that we could use for this, and we're not going to teach all that, but we'll sometimes refer to results of this type. All right, so in principle, Knuth tells us that accurate mathematical models are available. In practice, we can get really complicated formulas. We also might need some advanced mathematics that the theoretician will revel in, but that maybe people learning algorithms for the first time might not be expected to know. In the end, careful, exact models are best left for experts. There's really a lot of things that can go on. On the other hand, approximate models are definitely worthwhile. And for all the algorithms that we consider, we'll try to communicate a reasonable approximate model that can be used to describe the running time. Sometimes we'll give the mathematical proofs, and other times we'll have to just cite the work of some expert.